All right, this is unit or section 5.5. We're looking at counting techniques. So we're going to solve some problems, some counting problems using the multiplication rule, using this idea called permutations, combinations, permutations with non-distinct items, and then we're going to compute some probabilities using permutations and combinations. So some of these words may be brand new to you, and so we'll definitely cover these in pretty good detail. But this is all about counting, because a big part of probability is being able to count the number of possible outcomes. So first, solving counting problems using the multiplication rule. So the idea of counting plays a huge role in many diverse areas, including probability. So we're going to look at some special types of counting problems and develop some general techniques for trying to solve them. And let's just begin with an example that demonstrates a general counting principle. So a fixed price diner at Mabenka restaurant provides the following choices. So for an appetizer, you have soup or salad. You get one or the other. Then you can see for entrees, you've got, looks like 4 different entree choices and then 2 different dessert choices. And the question becomes how many different meals can you order? And one way I like to do these, and again, these are exclusive ors. You can only get one or the other. You can't select 2 appetizers, 3 entrees, and a dessert or anything like that, just for simplicity's sake in what we're doing here. So the idea of how many can we order, I usually, when I'm looking at these, I'll create little slots. I'll just do little lines. Those are supposed to be straight, but we'll go for it. So first choice, we have to select an appetizer. So you got 2 choices. So I'm just going to put in the appetizer column, I got 2 choices. Then you got to select an entree. Okay, in the entree, you've got 4 different choices. And then lastly, for dessert, you have 2 different choices. Okay, so now we've identified how many choices we have, but the question is for each individual category, but the question becomes, how many different meals can you actually order? Well, here's a picture. We'll come back to what I had just a moment ago. Tried to fit it all on one screen. But here's where you start. So here's kind of you're just looking at the menu, and then say you choose soup. Well, once you choose soup, you've got 4 choices: chicken, patty, liver, or beef. Say you go with the beef. And then once you've chosen beef, let's say you go with the cheesecake. So you get this setup: soup, beef, cheesecake. That is one possible outcome. Okay, now you could have said, well, actually I want the ice cream, but I still want the soup and the beef, so then that puts you here. And so then we could count through, and if you count up all of these different choices, okay, you'll see that there are 16 different possible outcomes. Now, the nice thing is, notice that 16 is the same thing as 2 times 4 times 2. And that's how you would determine the number of outcomes without having to draw this gargantuan picture. Okay, you simply take the number in each section, so appetizer, entree, dessert. You count how many are in each section, you multiply them together, and that tells you how many different, in this case, how many different meals you can have. Okay, so that's one principle of counting, the multiplication rule. So the multiplication rule of counting in general. So if a task consists of a sequence of choices in which there are P selections for the first choice, Q for the second selection, R selections for the third, and so on, and it just keeps going, you just multiply those things together. And that will be how many different ways you can count something, or how many different outcomes there could possibly be. It's the multiplication rule. But again, that's when you only have one selection in each sequence of choices. So we've got a woman here who has 5 blouses, 3 skirts, assuming that they all match. How many different outfits could she wear? Well, so we have the blouse is going to be 1, And then the skirts are going to be another. And she's got 5 blouses. She's got 3 skirts. And we simply multiply 5 times 3, and there will be 15 different outfits that this woman can put together based off of the 5 blouses and the 3 skirts. Again, assuming that everything matches. Okay, so that's the multiplication rule. Now let's look at one that might be a little bit more in depth. So we're forming some license plate numbers. You see these all the time, and we want to know how many different license plates can be made using one letter followed by 5 digits. And again, then your digits have to be 0 through 9, which is 10 digits, because 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, so 10 digits. So how many different license plate numbers? Well, so the first one has got to be a letter. And then that is going to be followed by 5 numbers. So 1, 2, 3, 4, 5. Okay, so all of these are going to be numbers, and that's a number sign, not a hashtag. Okay, so the numbers and the letters, they're each individual selections. So there are 26 letters in the alphabet. So you have 26 letters in the alphabet. And then the numbers, there's no restrictions on our numbers, so it doesn't say you can only have one number occur once without repeating. So there are 10 digits for the first one, 0 through 9, 0 through 9. So there are 10 choices in each of these columns or selections. So then I would just multiply all these together, and that would give me 2.6 million. So 2,600,000 different choices of license plates when I have those parameters. A letter followed by 5 numbers. Okay. Now, we're going to look at this idea called a factorial. And this will be very helpful for a lot of problems that we're going to get into. But let's identify what this means. So if n is greater than 0 and is an integer, then the factorial symbol, n with an exclamation mark, okay, that's how we identify a factorial as an exclamation mark, is defined as the following. So n factorial is just n times n minus 1 times n minus 2, blah, blah, until you get 3 times 2 times 1. I will go more into that, but it's just that number, say it's 20, times every number below it. 20 times 19 times 18 times 17, 16, 14, all the way down to 3 times 2 times 1. These factorials are huge numbers and can get huge fast. And then the definition of 0 factorial is it's equal to 1, and 1 factorial is also equal to 1. That's by definition of a factorial. Okay, so we want to find the value of 10 factorial. So this would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Massive. And that will be 3,628,800. Again, factorials get big, and they get big in a hurry. So you can use your calculator. You're just looking for the exclamation mark. You may have wondered, you may have come across it on your calculator, and now you're like, oh, that's what I would use it for. So you would just simply type a 10, then the exclamation mark, and enter. It should spit out this number. Okay. Now, what use would this have? Well, let's take a look here. What if we're trying to arrange students? We've got 15 students, and we want to know how many ways can we line up the 15 students. Okay, so again, I'm just going to think of these as individual slots. So student 1, 2, 3, 4, 5, and it's going to keep going. So there, you have 15 students to choose from in the first selection. But once you've selected that first student, the second choice, there's only 14 students remaining, so you only have 14 choices there. Then there's 13 for the third, 12, 11, and this will keep going down until you get 3, 2, and then finally the last one. So you can multiply all those together. So instead of just saying 15 times 14 times 13 and having to multiply all that together, this is simply 15 factorial. And you can plug it into your calculator and you get 1 point. This is, I'm going to write this in scientific notation because it's so big. 1.3076 times 10 to the 12th. So we're up, I believe, in the trillions of ways. If you have 15 students, of the number of different ways you can organize those 15 students or line them up. So again, factorials are massive. So don't try and type like 100 factorial in your calculator. You'll most likely just get a memory error because it's just too big. Okay, so we're going to be using factorials in this idea called a permutation. Okay, permutation is an ordered arrangement. So big key word to go with permutation is order. Order matters in a permutation. So a permutation is an ordered arrangement in which R objects are chosen from N distinct or different objects, where R is less than or equal to N. So, for example, there's like 20 racers and you have 3 places on the podium. So N would be 20 and the podium places would be 3. So the number of things you're picking from has to be greater than the number of outcomes that we're looking for. And repetitions are not allowed in permutations. The symbol, it's going to be an NPR, represents the number of permutations of R objects selected from N objects. Okay, so now let's look at this little question I got right here. So we're going to consider the letters A, B, C, and D. How many permutations of 2 exist? And remember that the order, when I say permutation, order does matter. Very specific. So let's just write out the possible outcomes. Okay. So you have to pick 2 from the 4. So you could do AB, or you could do AC, or you could do AD, or you could do a BC. You could do a BD. I could do a CD. I could do a BA. Notice that that is different than AB because order matters. B comes first in this one compared to the previous. So BA, I could do a CA, I could do a DA, I could do a CB, I could do a DB, or I could do a DC. And so if I count all of those up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there are 12 different outcomes. Okay, but again, the order matters. We're going to get into something called combinations later where the order does not matter. So like A, B, and BA would be considered the same thing. But in permutation, the order matters. A, B, and BA are different in permutations because the order is very specific. So the way we would write this is we would write this as we had 4 letters and we are looking at 4 permutations of 2 because we're picking 2 of the 4 and that was equal to 12. And that's the notation that you will see. So here is numbers of permutations of n distinct objects taken R at a time. Okay. So a couple of things. N objects that have to be distinct. You have to be able to distinguish one from another. Repetition is not allowed. Once you use it, you can't use it again. And order is important. Oh man, I cannot stress that enough on permutations. If that's the case, then NPR, n permutations of R, is calculated as n factorial divided by n minus R factorial. So in our case, you had 4 factorial because we were choosing from 4 letters, and then we had 4 minus 2 because we were selecting 2. So 4 minus 2 factorial, which is 4 factorial divided by 2 factorial. And this is just a very simple example. So 4 times 3 times 2 times 1 over 2 times 1, and the 2's cancel, the 1's cancel, so you get 4 times 3 is 12. So the cancellations will work out very nicely. But just know that that's the formula. You don't have to know exactly where the formula comes from. You just need to be able to calculate these things. I'm going to show you how to calculate them in the next video. But I appreciate your time as we went over this part 1.